Okay, so today we're just going to be going over some of the questions that you were assigned the other night, and if you have any further questions, we could talk about them the next day. Alright, so this is our practice on angular kinematics. So the first question that we're going to address is a turntable radius R1 is turned by a circular rubber roller of radius R2 in contact with its outer edges. So we have something like this. We have a smaller turntable, and it's in contact with a larger turntable. This is our R2, this is our R1. So that distance right there is R1. And we want to know what is the ratio of their tangential speeds. Well, since they're in contact, that when this one is moving, let me do this in a different color, that since they're in contact, whatever that V1 and that V2 is, they have to be equal. Because otherwise, if they were not equal, there'd be some slipping. And we're assuming that they're using together as a unit. So with that in mind, if we want to know their ratio of their angular speeds, omega 1 to omega 2, and we know that V equals omega R, that means omega is equal to V over R. This means that we have V1 over R1 over V2 over R2. And since V1 and V2 are the same, I get 1 over R1 over is equal to 1 over R2. And if we copy, change, flip this, we get R2 over R1. And that's our answer. The next one, we're dealing with a smaller wheel of radius 10 centimeters rotating at 2 meters per second. The larger wheel has 3 times the radius. What is the angular speed? So same idea here, that the tangential speed that's going right there, that V has got to be equal to that V. Otherwise, if this were like gears, the chain would be building up here faster than it is here. So that can't happen. So V1 is equal to V2, which if we go back up here, that if V is omega R, this means omega 1 R1 equals omega 2 R2. And a cool way of looking at this, if we have a wheel that's got 3 times the radius, and we want to know what is going on with its velocity, we could say, what fraction is its angular velocity. So we have 10 times 2 equals omega 2 times 3. Okay, actually 30, 3 times the radius. So if you divide by 30, we get omega 2 to be 0.67, and since this was in revolutions per second, this is in revolutions per second. And if we want to convert that, this is 0.67 rev per second. We want to convert that to radians per second. 1 revolution is 2 pi radian, so that gets rid of the revolutions, and 60 seconds is 1 minute. Okay, so that gets rid of the seconds. So what we would do is we multiply by 2 pi. That would get us in no, we don't have to do this. We just multiply by 2 pi because we're already in now radians per second. We were just trying to convert the revolutions to radians. And if you do that, I got 4.2 rad per second. The next example is a woodworker cutting a piece of wood with a circular saw. A saw blade accelerates from rest, so omega naught equals 0, with an angular acceleration, so alpha equals 15 rad per second squared, to a maximum speed of 12,000 revolutions per minute. And notice that I'm writing it like this, because actually what I want to do is I want to convert that. So get rid of the revolutions, put them down below, get in the radian, and just like before, 2 pi radian is 1 revolution, and then get rid of the minutes, so put that up above, get it into seconds, and 1 minute is 60 seconds. So my minutes cancel out, my revolutions cancel out. I do 12,000 times 2 pi, and then divide that by 60. And that gets me a angular speed of 1256, and that is rad per second. And that's my answer. How much time does it take? Well, I have the acceleration, and if I want to know what time is, my acceleration is my change in angular velocity divided by time. So that means that my time is my change in angular velocity divided by acceleration. So I get a change of 1256 divided by, and that's rad per second, divided by my acceleration of 15 rad per second squared. And that gets me a time of 83.7 seconds. If we want to know how many revolutions it makes while accelerating to its maximum speed, so I'm going to find my angular displacement. So I'm trying to find my theta. And I want to get into many revolutions, but I'm going to first find out how many radians. So I know the kinematics equation, my change in angular displacement is omega naught t plus 1/2 alpha t squared. Omega naught t is 0 since we start off from rest, and I get 1/2 times my angular acceleration, rad per second squared, times my time of 83.7 seconds. And that gets me 52,500 radians, and if I convert that to revolutions and round it to 2 sig figs, I get 8,400 revolutions, and that's my final answer. And the last question here, the safety mechanism gets the blade in 0.4 seconds. What is the angular acceleration? Well, it's just like before, we have an angular acceleration as a change in angular velocity divided by time. So this is my 1256 divided by my new time of 0.4 seconds to get an angular acceleration of 3,100 rad per second squared. Number 4 is a bicycle slows uniformly from initial speed, so of 8.4 meters per second, to a rest over a distance of 150 meters. So initial velocity, this is initial velocity, linear velocity, 8.4 meters per second. To rest, so final velocity 0, and my displacement is 115 meters, and we have an R of the wheel of 0.7 meters. So if I want to know the initial angular velocity, well, V equals omega R, so omega equals V by R, and I get 8.4 divided by 0.7, and that gets me a initial angular velocity of 24 rad per second. Total number of revolutions each wheel makes before coming to a stop, well, I know it travels 115 meters, so that is my delta x. So delta x equals theta r, so theta equals delta x by r. So I take my 115 meters, I divide it by my 0.7 meters, and so that gets me a 329 rad, and then I convert that to revolutions, and I get 52.3 revolutions, and that's my final answer, because I'm asking for how many revolutions. So in other words, the bicycle wheel has to go around a little over 52 times in order for it to cover the 115 meters. Angular acceleration as it stops, well, my angular acceleration is my change in omega divided by time. So my initial velocity, angular velocity, is this. My final angular velocity is 0, so that is 24 rad per second divided by my time, which we don't know. So what we can do, if I erase this here, that's not an eraser. What we can do is we know omega squared equals omega naught squared plus 2a alpha delta theta, and the final angular velocity is 0. So I have this. I have I'm trying to look for the angular acceleration, and I have my change in theta. So if I rearrange this, I subtract the 2 alpha delta theta, and that is equal to omega naught squared, and then I divide by the negative 2 delta theta, divide by the negative 2 delta theta, and I'm going to bring that negative outside of the parentheses because my angular acceleration will be negative, and I don't want to include that negative in the square root. And so that cancels out there, and I get an alpha equal to 0.88 rad per second squared. Now the time, well, the alpha is equal to change in omega divided by time. So if I rearrange that for time, time is equal to change in omega divided by alpha, and my change in omega, my change in angular velocity is 24 rad per second, and I divide that by my acceleration of 0.88 rad per second squared. That gets me a time of 27, a little over 27.4 seconds. And if I ask myself what part of the wheel tire is moving at 8.4 meters per second, well, if I think about it, I first related the angular velocity to the radius. And so it's actually the outer edge that's moving at that 8.4 meters per second. That is the tangential velocity of the bicycle. So it's the outer edge, so the tire, if you will. The last question here is a test pilot in whirling human centrifuge, which takes 1 minute and 20 revolutions before reaching its final speed. So what is the angular acceleration? Well, I know a time of 1 minute, which I really want 60 seconds. I know a change in angular displacement of 20 revolutions, and if I convert that to radians, that's 125.7 radians. You start off at rest. So the angular initial velocity is 0. And I'm looking for the angular acceleration. So that's what I'm trying to look for. So delta theta is equal to omega naught t plus 1/2 alpha t squared. And if I cross off my initial angular velocity and I solve for alpha, I multiply both sides by 2. That cancels that out, and then I divide by t squared. So this actually looks very similar to when we first were finding the acceleration of linear acceleration. So my alpha equals that. If I plug and chug, you should get an angular acceleration of 0.07 rad per second squared. And I'm going to change this actually a little bit. Nope, never mind. The final angular speed in radians per second squared, well, if I think about, there's a couple different ways I could do this. But I think the most obvious way is that is your average angular velocity in revolutions per second. So that is 20 rev per minute. And if you convert this to radians per second, so 1 rev is 2 pi radian, and 1 minute is 60 seconds, that gets you a angular speed of, actually I didn't do this, no, this will be about 6 times 2, okay, will be 12, so we get, and divide by 60, we get something in the ballpark of 40-ish, but I'll leave this up to you to actually finalize that. The final linear speed, I'm sorry, this will be 4.2 radians per second. Okay. But check my math. The final linear speed is equal to the final angular speed times the radius. So if I have 4.2 rad per second, and I multiply that by my r of 4.1 meters, that gets me a final linear speed of 17.2 meters per second. And the last question here is how many g's of acceleration can be experienced at the final speed. I'm looking for a radial acceleration, because that is the inward acceleration. That's going to be the big one that the pilots are feeling, and that's your v squared over r. Okay, that's our centripetal acceleration. So we have a 17.2 meters per second divided by my radius squared, divided by my radius of 4.1 meters. That gets me an acceleration of 72.2 meters per second squared, which if I divide that off by 9.8, I get 7.4 Gs. That's a big, especially for a whole entire minute. All right, so that's all for now. Thank you for listening. I hope this helped clear up some things, and have a great rest of your afternoon.